My name is Steph Evans and I'm the lead FEA engineer at Evotech CAE Ltd. This video makes up a tutorial from the 101 series and is focused on a number of aspects of 2D modelling and FEA within Apex. Okay, so in this example we're going to be looking at the development of a 2D model for downstream shell meshing and analysis. So we brought a typical bracket, maybe seen in an aerospace type structure, into the Apex environment from external CAD source. So just measuring the geometry, we can see we've got lots of thin walls which lend themselves to 2D shell elements. Obviously we could look at this as a 3D model, but for the purposes of this exercise we're only interested in the overall stiffness of the structure and maybe the fastener loads. So mid-surfacing, so starting off by picking some faces using one of the mid-surfacing tools in Apex, auto offset. So literally just pick the faces and middle mouse button to accept, and we've got the mid-surfaces generated automatically. If you've got a structure with lots of mid-surfacing to do, then the incremental mid-surface tool is perhaps a better option, and this can be used to highlight a given solid or series of solids, and Apex will then automatically define a series of mating surfaces which will be used to represent the underlying mid-surface. So we can see here we've got a mid-surface pair at the bottom of the bracket. We want to take out some local details such as fillets and small surfaces out of the structure, or out of the pair rather, so that the underlying surface is created without any local bumps where the fillets exist. So we work our way around the model with the automatic pair definition, and then some manual edit to those pairs to give us the underlying mid-surfaces that we want. Once we're happy with the pairs, we can select and middle mouse button to accept, and we've created the underlying mid-surfaces. So you can see in this example it's pretty much a flat type structure, but this works equally well for curved surfaces as well. So once we've got those mid-surfaces, we can use the auto extend geometry function, and that will snap edges to faces or edges to edges within a given search tolerance, and quickly we can build up the underlying full mid-surface for the structure. You can see that red edges are free edges, green edges are shared by two surfaces, and yellow edges are what we call manifold edges, which are shared by more than two surfaces. So just some push-pull standard Apex type operations to snap edges together. These particular edges we were looking at were outside of the extend surface tolerance. We could have upped that tolerance, but you can see we've got manual control as well. Putting the underlying 3D CAD geometry back on, back in view rather, we can then vertex or edge drag the surface edge to meet the face of the underlying solid, so the fillet in this case. Done that for two regions, and when we take the original solid out of view, we can see that the new surface is generated respect that surface that solid geometry, I should say. So a little bit more edge dragging, vertex dragging, using the guidelines to control the surfaces as we work our way around the structure. We could have meshed this structure first with shell elements and used the element quality to pick out any areas which are potentially poor topology, but in this fairly simple example we will do the obvious edits first of all. So shell meshing first of all, you can see reasonable job using the mixed quad and tri shell elements, and we can put the element quality checks on. We've got a large proportion of good quality elements, no invalid elements, some local changes we might wish to make. So the first thing we're going to look at is the removal of the smaller fastener holes. So we can do this with the defeaturing tool, the auto defeaturing tool. So Apex will pick out, in this case, holes of a given diameter, so we can see that it's picked out two sets of holes. We can highlight the smaller holes, click the create seed point checkbox on, and all the points that are created are effectively seed points or hard points that the mesh then respects during the automatic remeshing operation. If you notice, we haven't had to remesh any geometry because of Apex's generative approach. We can see that everything's updated automatically and washed downstream through the model definition. So putting the underlying solid back on again, we're now going to use this for some local edits. So we can see here there's a thicker region with a fillet which we need to respect within the mesh. So we're going to split the underlying mid-surface, so remove the, or hide from view, the face of the solid, pick the split line, and then apply that to the mid-surface. The mesh is automatically updated, again based on the generative nature, and we can see the changes that are made as we go through. So again, vertex edge drag, and we can quickly update the mesh to give us the cut or the split lines that we want. Again, just simply dragging the vertices along the guidelines to make sure everything is as we want it. So we can see here the paver mesh has done a reasonable job in respecting the fastener positions, but we've got some I would say randomness, if you like, to the mesh, so we can quickly split the surface along those fastener definitions or fastener seed points and remove a couple of vertices, and we've got a very nice quad mesh that respects the underlying fastener definition. So we're going to do that at the other end of the bracket. So again, picking the surfaces we want to edit, the split line hitting the fasteners and the vertices on the edge of the surfaces, and again remeshing automatically to give us a much better definition. Again, remove a couple of vertices, and we've got a very nice element quality in that region. And again, we can put the element quality fringe plot on. We've got no invalid elements, a couple of poor and bad elements in areas we're not interested in, but we could make some local changes to modify those if necessary. So taking the geometry out of view, we're going to look at some standard mesh checks. So first of all, we can look for cracks in the mesh. There are no cracks. We can look at the edge topology, similar to the way that the geometry is handled, but we can see what the mesh is doing. So we've got shared, free, and manifold edges. Looking at shell normals, so color coded in the first instance. So rather than populating the whole space with lots of vectors, it's difficult to make sense of. Apex gives us the opportunity to view the normals as red or blue faces depending on the surface orientation, and we can flip those surfaces based on picking some of the candidate elements for a given surface. We can put the element coordinate system on, we can show the element normals once we've made the changes and we're happy with that, and we're good to go. So very quick, very generative, so minimal effort in terms of mid-surfacing, meshing and mesh controls to get to this point. So auto thickness, so again putting the underlying CAD definition back in view, and we can use the automated thickness tool within Apex to develop the thickness for a given surface based on the projected normal with the underlying CAD definition. So you can see here, very quick and easy. We can switch to section view, which gives us the opportunity to look at the model based on a color-coded shell property definition, and we can see at this bottom region we've got a surface which has taken the incorrect thickness that we want based on the underlying CAD definition. Some of the local fillets from the underlying CAD can influence the resultant properties, but we've got means of going in either on an automated or manual approach to update those property definitions. So we can see working our way through the model, and again we've got the top part of the bracket. We're just going to reassign some of the local shell properties for a given surface that hasn't quite picked up what we want, again skewed by some of the fillets in the underlying CAD definition, but we can tidy up the geometry. We're happy with the definition, switch back to model view, and then put the shell thickness on display, and we can see that we've got a much better representation of the shell properties. With the underlying CAD shown, we can and in transparent mode, we can look at the shell thicknesses versus the 3D CAD display. We've got a very good and quick to this point definition for controlling those things. As with everything in Apex, we can do an analysis verification, so quickly run a free normal modes analysis to double check we've got the response that we want. We can look at various shell outputs, so in this case we're looking at shell forces, equally look at shell stresses, shell moments, that type of thing. So all the standard tools that we or output quantities that we'd need, von Mises, max principles and components in any system that we're interested in. We can look at 2D shell output, so we can look at either layer, we can look at the average, we can look at the maximum, the minimum, that type of thing, and then we can look at some of the nodal output, So averaged shell definition, which is basically shell elements results averaged at a given connection node. We can turn averaging off, and we can do difference plots, which can be used to understand the jump in stress from one element to the next, and give us an understanding of how good quality the mesh is for what we're looking at. So a simple example here, based on, again, on the generative nature of Apex. So we've got a plate with 3 holes in it. We've fixed at one end, we've got a applied load or displacement at the other end, and we've got the underlying CAD definition which we've used to populate the shell properties. So we're going to do a quick analysis of that structure, and we can see again run using the embedded solvers with Apex. This can be for a full analysis or a verification run prior to external solution with another tool set potentially. So we can look at the stress response animated plot, so we've got a good idea of what the structure is doing, and some idea of what the stress levels we would expect for a given geometry, or a given set of dimensions for that geometry. So what we're going to do now is make a subtle change to the underlying CAD definition. So we can either modify the CAD within Apex, or we can bring in a Mark II CAD, if you like. But basically what we're going to do now is modify the fastener diameters based on the 3D push-pull operations in Apex, just increasing the fastener diameter to give us bigger hole clearance, just working the way through the 3 holes. Once we've done that, we can then use the vertex edge drag tools and simply snap the face of, or snap the edge of the hole to the new face of the 3D geometry, and the mesh is updated. When we turn the mesh, turn off the solid from view, we can see the mesh is updated. So we've got new holes, new mesh, good quality control of the mesh definitions. We've got washers around the holes, etc., and we can rerun the analysis very quickly with minimal input. Okay, thanks for watching this tutorial. Be sure to keep an eye out for the remaining tutorials in the 101 series to illustrate how Apex can help with your FEA process.